physics.
Particle physics. So we're now into, guys, the last.
I have exam waiting.
Guys, we're now into the last 3 chapters. I kind of shove them all together. This is
What? I thought last week was
29, 30, and 31. Those are the last 3 chapters we need to cover before the AP exam.
Oh, I'm scared.
And my goal is always to be done with that by spring break, and we're really, really close. That's why I was trying to push to get us to take that test on Friday, and it just wasn't going to quite work. We'll at least be done with content. There's one year it was so bad that they did chapter 29, 30, and 31 as independent study over vacation, and that was a total disaster, and I will never do that again. So nobody did anything, and it was bad. It was really, really bad. So chapter 29 is on particle physics, and so the thing you need to understand is that everything we've looked at so far. Wait for Kate. Everything we've looked at so far, we've considered light to be a wave, right? We looked at its wavelength. We've looked at its frequency. We've considered light to be a wave. But it's also a particle. So this is the chapter we get to see how strange light is, and that light actually acts like a particle and a wave all at the same time. That's the wave-particle duality theory, right? Duality. That is both things at the same time. Because for a while people said, oh, no, it's a wave. And then for a while people said, no, it's a particle. Because it behaves like a particle. It has momentum. Light has momentum. Light can run into something and make the other thing move. And that seems bizarre because it has no mass.
I was going to say, but how can light have momentum?
Exactly. That's what everybody said. They said, well, how can it have momentum? It has no mass. We're going to figure out how you can calculate the momentum of that light particle. And then we go backwards and we look at a particle like an electron, and we figure out that it acts like light, and it can have a wavelength, even though it's a particle. Right? So it's it's the fact that these things can act both ways. So when we talk about photons, and in the activity you're going to do in a moment, you need to understand that a photon is a particle of light energy. And it's given off in packets. So this is supposed to be my pictorial picture of showing like a little photon particle. I have no idea what it would look like. And so the energy of one photon, E sub P, is equal to H times F. H is Planck's constant. I think Planck's constant has a C with it, though, doesn't it? I'm pretty sure it's
I think it does.
Planck's.
And he has a pretty badass muscle.
Planck's constant, not Planck's constant, but that's besides the point. And Planck was the guy who first figured out what this number was. And it's very, very small. It's 6.626 times 10 to the negative 34th joule seconds.
Oh God, he's an old white guy.
Did you find a picture of him?
Yeah.
I know, all the scientists
Does
are
he look
old
like
white
John
guys. What do you
C.
want me to
Calhoun?
say?
I don't know who that is.
But
Ask Ramsey.
But notice it's in
Ask
joule
Ramsey who John
seconds.
C. Calhoun is.
Guys, it's in joule seconds. Do you remember an electron volt?
Yes.
Remember electron volts? They also have Planck's constant in electron volts. It's like 4.14 times 10 to the something electron volts. Seconds. So what you find is sometimes you want to use electron volts and sometimes you want to use joules. Just make sure whichever Planck's constant you use is the one that goes along with the problem you're doing. Right? But if I have one photon, right, my light is up there, it's emitting a whole bunch of photons every second. In the simulation you're going to do, you're going to see little particles flying. Well, no, those are electrons. I take it back. The light, you're not going to see the photons. But the light is going to come in, but it comes in as these little particles. And each one of these little particles that you can't see, visualize, or anything, each of these little particles has an energy equal to HF. You can have more, you can have less, but each one is equal to HF. So if I make my lights brighter, so Owen, make our lights brighter. Okay. Owen is going to brighten us up. Now, assuming that this is all the same light, which is pretty close to it is, I did not change the energy of a single photon that's getting to your eye. All I did is I made more photons get to your eye. Right? Or Owen did, because he has the power to do that. So if I turn on the light, more photons are hitting your eyes, and you perceive that as being brighter. Now turn off the 2 and leave just the 1. So now, same energy stimulating your receptor cells in your eyes. They each have the same amount of energy, so your eye can say, oh, that's light, I can see. At HF, but there's just less of them hitting your eye. What's going to have more energy, red light or blue light?
Blue light.
What's going to have more energy, ultraviolet light or radio wave?
Ultraviolet.
Ultraviolet, right? So different types of light, you know exactly which one has more energy. However, you can turn the intensity up of any of them and get more photons. But that is how much energy one bundle coming off of that type of light has. Yes?
Is there light where like it has such high frequency that each photon carries a whole joule of energy?
It carries a whole joule?
Yeah.
Well, no, because every, well, you'd have to have a frequency of 10 to the 34th. And I don't think anything that I know of has a frequency of 10 to the 34th, right? Or a little tiny bit
What does
less.
that mean? What do you mean like a really big?
Yeah, because like visible light is times 10 to the 14th or so.
I never
Would it
heard
go
that.
like faster?
Yeah, it would vibrate faster.
Oh god, it'd be like.
I mean, that'd be like so. It would be so high, we'd probably all explode. Would
It'd
we
be
just?
faster than this.
Yeah, I don't. I can't even fathom how fast that particle would be vibrating. Yes.
But even then, would that theoretically be possible?
I don't think so. I don't. As far as I know, the highest frequency. You know, you guys are asking me good questions. But the highest frequency that I know of is like gamma, right? No, there's something past gamma. Cosmic.
Yeah, it's cosmic.
But cosmic. I don't know what does it say? Did you look? Does it say what the frequency of cosmic is? What's the frequency of cosmic? I know visible is like 10 to the 14th. I'm going to say maybe it goes up to 10 to the 20th, 28th. Does it go up to that high?
Yeah, it's so fun.
Does it say?
Give me a moment.
Ramsey's looking for us.
Most of them are probably that's one.
Does this one?
He doesn't say? You can't just type in frequency of cosmic rays and it just pops up the answer?
The West is kind of like.
It goes up to
I think it does one. Like
300 E-hertz.
E-hertz? What the heck is an E-hertz? I know what a gigahertz
I
is.
think it's above, it's whatever it is, it's above
Exahertz.
petahertz.
What's that?
It's an exahertz.
Okay, but what's an X?
I don't know, it's above a petahertz. All I know, the highest I have on this